Okay, I want to do one more lesson on Taylor series because there's just so many cool things you can learn from them and do with them. So I'm going to kind of pull together some of the things. This is the where we ended up with the last lesson, and I'm going to take this and run with it a little bit. So first of all, if you took my challenge and found the Taylor series for this thing, you would have found, hopefully you did find, that the Taylor series is just this. Agreed? That's the Taylor series. That's the geometric series. And we showed earlier that basically you can only have one power series that converges to a function. So there it is. And we know that that one there is good for x less than 1 in size. And you can, let me bring this one up here just to get rid of it a second. I'll keep it in mind. And it's easy to see why the radius of convergence of this thing is just 1. Because if you were to graph this function, I'll do it over here. Here's what it looks like. Let's see. It has a vertical asymptote has a vertical asymptote at 1, right? It has a vertical asymptote at 1. Here we are. I did it wrong when I was practicing it here. So here it is. Here's 1 right there, x equals 1. And what happens? Let's see. When x is 0, the value is going to be 1. You get something just a little bit less than 1. And this will be a very, very large number, so it's going to go up like this. Apparently it's going to go down like this, and then it kind of comes up like this and heads off like that. So there's the graph of it. So it's easy to see why things go haywire once you pass 1. You start there at 0, and you can go out as far as you want. Keep going out farther and farther until you bump into this discontinuity there. And at this discontinuity, the function goes off to infinity, and so everything goes haywire. So there's nothing. This is in another world over here. So that's why it stands to reason that the radius of convergence is just going to be 1 heading out from 0. But let's with that in mind, let's get rid of this picture and recall what we did a couple lessons ago. We took this thing and we played with it, and we first said let's let t be equal to negative x. In fact, it might be easiest just to let negative x be equal to t squared. I think that'll do it. Be equal to t squared. Let's do that all at once. So x is equal to negative t squared. Okay, so let's go ahead and do that. So every place I see an x, I'm going to put a negative t squared. So negative x is equal to t squared. So it's going to be 1 plus t squared right there is equal to x is equal to negative t squared. So it's going to be negative t squared to the n power. And that's going to be when x, which is negative t squared, is less than 1. But you can bring this negative out and it doesn't affect anything. And the absolute value of t is less than 1 exactly when the absolute value of t squared is less than 1. So this has the same radius of convergence as the original right there. Okay, and so this thing right here now converges to that. So you look at this and you say, okay, here's another power series that converges to a function. And so again, if you were to actually calculate the Taylor series of this thing, evaluated at 0, this is what you would get. So so you look at that and you say, okay, that's all fine, but then you look at this function and you say, what does that look like? That's as nice and smooth of a function as you're ever going to want. It's called the Cauchy distribution. Okay, 1 over 1 plus t squared. Notice that it's going to have a maximum value when t is 0, and it's going to head off in both directions there. This is now the t-axis, I guess, rather than the x-axis. So now you ask why, or I ask, an astute person would ask, what's the problem with this? It's nice and continuous everywhere. Why does this have a radius of convergence only of 1? Because there's certainly nothing bad that happens, no discontinuity, no sharp corner, no place where the derivative is undefined or anything else as you head out from 0. Why does this thing have that same restriction that the other one did? And you can tell that it does have that restriction because if you stick in 1/2 here, this thing will converge to this. But if you stick in 2, then this is going to be what? If you stick in a 2 here, you're going to get 1 over 1 plus 1/4, which is what? 1 over 5/4, which is 4/5. But this side, you stick a 2 in there, and this thing doesn't converge. It goes wild. Okay. So what's wrong? Why doesn't this thing converge to this? Just given the fact that this function looks so nice and smooth, what's the problem? And the answer is just really profound, okay, or insightful, I guess. The answer is that even though we think we are living in the world of real numbers and we limit ourselves in calculus to the real numbers, in fact, we are like a horse with blinders on. And really, we are living in the world of complex numbers without even knowing it. Okay, that's why if you remember the fundamental theorem of algebra, it basically says that if you have a polynomial, an nth degree polynomial in the whatever you want, x cubed plus 3x plus, or x squared plus 17x plus 85 halves, or 85 pi, or whatever you want, that thing there can be factored into. Okay, the video stopped and I caught it just in time here. So this thing can be factored into x minus something and x minus something and x minus something. As long as these things are complex numbers, you can do it. If you're over the real numbers, then if you have x squared plus 1, for example, there's no way to factor that. Then only the best theorem you can have is that anything like this can be factored into linear terms, things like this, and then quadratic terms, things like this. So the point is, it's a much more beautiful theorem if you state it over the complex numbers, because then you can say an nth degree polynomial can be factored into n factors, and so you have this beautiful result. So there's one example where you kind of get a hint that the real world we live in is the world of the complexes, even though for our purposes we really don't need the imaginary numbers all that much. The only reason we don't use them more is because we just don't need them more. If all we needed was positive integers, that would be our world. But we need negative integers, and we need rational numbers, and in order to talk about calculus things, we need the whole real numbers. And so that's what we have. But electrical engineers and some physicists and so on, they need the complex numbers as well, and so they're there. The word imaginary is a poor word because it gives you a sense that these things aren't legitimate, but they're just as legitimate as anything else. The number 3 is a legitimate number in the sense that you can come up with 3 different things in your hand. Okay, there's 3 different things. But as soon as you get even to negative numbers, you can't show me negative 3 things in your hand. As soon as you get to negative numbers, you're already in an illegitimate world, right? You're not in the real world anymore because it's an imaginary world, okay? Negative 3 things, a debt of negative $7 or something like that, okay? So it's all just a world of mental things as soon as you get to negative. So imaginary numbers are no different than that. They're numbers that just aren't as useful as the other ones we use. So that's a long way of saying that the complex numbers is the real world we live in, and this is another place where that shows up, because if you look at this thing and ask where does that thing go to 0, this thing here went to 0 at 1, and so that's where this function blew up. That's where it had a discontinuity, was at 1. This function here blows up at I and negative I. Okay, that's on the complex plane. On the complex plane, I is 1 unit up and negative I is 1 unit down on the imaginary axis. And so what's really happening is you start from 0 here, and instead of just kind of going out along the x-axis until you reach a bump, you're really going out in all directions. Even though you don't realize it, you're going out in all directions until, boom, you hit a bump there. There's your bump. There's your discontinuity that happens at I, and that's why you can only go out 1 unit in both directions before things go haywire. Okay, so beautiful stuff you learned from Taylor series. So there's the first thing I want to show you. So very good. Okay, so I'll erase all this stuff now. Okay, now let's go to this one next. If you think about what the ln looks like, here's the ln of x, and so it's clear that we can't form a Taylor series about 0 for the ln of x because it's not even defined at 0. So what we did with this function, this was a couple sessions ago where we found a power series that converged to that, which would then be the Taylor series. What we did was we took the ln of x and we shifted it over 1. Agree? If you shift it over 1, it's now going to go through this point, and it's going to look like that. And we found the Taylor series for that, and we could do it again. That would be a good one to do. But let's do this instead, just to get a little practice. Get a little practice at things. Let's go ahead and take the original function ln of x right here, and let's expand it about the point x equals 1. Okay. Here's our Taylor series centered around 0, but recall we can center it around anything, put an a in there, and make this an x minus a right there, and there we have a Taylor series about the point a. Okay, so let's do that for this particular one. Let's see once what we get. Okay, see once what I have. Boy, I wish I had more. I wish I had twice the room here. What's the saying about if wishes were something, beggars would be kings? So anyway, here's our function. So here's our function. F of x is equal to the ln of x. And so we're going to first take these derivatives, and then we're going to apply them all at the point 1. So let's take the derivative here. Here's the first derivative, which of course is 1 over x. And here's the second derivative, which is going to be what? Minus 1 over x squared. Is that right? Over x to the negative 2, rather. And here's the third one, which is going to be a positive 2 over x to the minus 3. The fourth one is going to be a what? Negative 6 x to the minus 4. And now, hopefully at this point in your mathematical Calc 2 career, you're starting to notice patterns. I could bring the 4 down and get 24, but I think it's much more instructive to write this is 2 factorial, this is 3 factorial, and now I'm multiplying by 4, so it's going to be a 4 factorial, right? 4 factorial, x to the negative 5, and this one's going to be positive again. Okay? Write that a little bit bigger. Positive 4 factorial, and so on. Okay? So now we evaluate each of those things at 1. Okay, we're going to do this at 1. So at f of 1 is going to be what? 0. F prime of 1 is 1. The second derivative at 1 is going to be negative 1. Then these are all easy. Stick a 1 in there. Then f triple prime at 1 is going to be a positive 2. The fourth derivative at 1 is going to be a negative let's write it a negative 3 factorial. The fifth derivative at 1 is going to be a positive 4 factorial, and so on. Okay? So, what's the Taylor series going to look like now? So here we are. This is the Taylor series for the ln of x. So I'll kind of go like this again. And this is about 1. So what do we do here? It's going to be, I don't know. I kind of like writing out the terms first rather than trying to do it all at once. Sometimes it's easier to do it all at once, but I like to write them out. That way you kind of make it into several steps, and then you finally see the pattern. So this is going to be 0. Then it's going to be 1 times x minus 1 to the first power when n is equal to 1, all over 1 factorial. Then it's going to be what? It's going to be minus. Here's the derivative here's for n equals 2. It's going to be the derivative, which is going to be minus 1 x minus 1 squared over 2 factorial. Okay, that takes care of this one. What about when n is equal to 3? You're going to get positive 2 times x minus 1 cubed over 3 factorial, right? Now the next one is going to be negative 3 factorial, there's the derivative, that's for 4, times x minus 1 to the 4th over 4 factorial. Okay, now it's going to be plus 4 factorial x minus 1 to the 5th over 5 factorial, and so on. Okay, very good. So now let's see if we can make this look a little nicer. So this thing we can just get rid of here. And this is just going to be an x minus 1 right here. Might as well just write it as x minus 1. Okay. And now this is going to be minus this thing over 2 right there. Then it's going to be plus. It's going to be this thing. Here you have 3 factorial. That I can think of as 2 factorial. And this divides out with this, just leaving the 3. Here you have 3 factorial. Here you have 4 factorial. So you just have an extra 4 down here. So this goes with all this, just leaving the 4. And you have the negative out front. Same thing here. You see that this is going to leave with all of this stuff, just leaving the 5. And now we see, I guess I can erase this now. We see the pattern, hopefully. So we have what? The ln of x, the Taylor series for it, is going to be, let's see, it's going to be, first of all, it's going to be powers of x minus a, or x minus 1 in this case. So let's write it like this. X minus n. Whatever this power is, notice that you have the same thing in the denominator. No factorials, they all canceled, but we have that same thing in the denominator. And then we have, we're starting at n equals 1, agreed, right here. And finally, we want something that alternates signs. So I want a negative 1 to the, let's see, when n is equal to 1, I want it to be positive. So I'm going to make this an n plus 1 right there. Okay, and so now when n is equal to 1, then this will be 2, and so this will be a positive number. When n is equal to 2, 2 plus 1 is 3, this will be a negative number, and so on. So there's a way to find the Taylor series about a point other than 0. Okay, and so if you look back to to what we had before when we found the power series that converged to this. It looked pretty much the same. It just had x's in there rather than x minus 1s because the whole thing was shifted over. Okay, so I'll let you play with that. And again, if you were to look at this, you say, okay, this thing obviously won't be able to make any sense beyond going 1 unit in both directions because you head out from here and you run into this discontinuity. See that? So this would only make sense, and you can prove this stuff using I'm not getting into that with Taylor series, how to show that it converges, but basically, as I told you earlier, it's going to converge as long as the function stays continuous and differentiable as many times as you want it, infinite number of times for as big of an interval as you need. So here, this function is totally well behaved. How far out? Until you get 1 unit out from your starting point. And so this thing is going to converge to that. It's not proved, but it is the case. This thing will converge to this on that interval right there. Okay, 1 unit out. Even though it goes farther in this direction, you're stuck. It's kind of like Einstein with when he showed about the fact that particles, when they split, that the future of this particle depends on this particle. There's this connection between particles that have been broken off from each other, and what happens to this one will instantly affect this one. And the same thing with power series. What happens here depends on what happens on that side. Okay, kind of a cool. Never had that thought before. Isn't that cool? It's 9 o'clock in the morning, and had a brand new thought. Okay, very good. So that's that one. So that takes care of that one. Now let's just see what we can do with some of these other ones. Okay, let's take sine of x, for example. So sine of x, recall this thing here actually equals its power series for all values of x. This thing converges for all powers of x here, and so we saw that the power series was this, or the Taylor series was this. And so on. So just showing you some things you can do. So that's the sine of x right there. So this is true for all values of x. So I can make this x look different. In particular, I can let x be equal to t cubed. Heck, yeah. Oh, let's make it t squared. So x is equal to t squared. So what does this look like? It's going to be the sine of t squared. Is going to be what? T squared minus, every place I see an x, I'm going to put a t squared. And so it's going to be a t to the, 6th over 3 factorial plus t to the 10th over 5 factorial minus t to the 14th over 7 factorial plus, oops, t here, t to the 18th over 18 factorial. Oh, let's see, what am I doing here? 9 factorial. Too many things to be thinking of at once. Okay, so you got that. Okay, so for example, what if I had this as a problem to solve? What if I was interested in the limit of the sine of t squared minus t squared plus t to the 6th over 6, period. No, all divided by t to the 10th. Okay, what if I was interested in that limit? Just to kind of show you what you can do with this. This limit is t goes to 0. Okay, what if I were interested in that limit? So, one way to do it would be to use L'Hopital's rule. But I can tell right off the bat here that you're going to have to use L'Hopital's rule 10 times here. And it could be getting kind of messy by the time you start taking this thing here and taking its derivative 10 times, even though you'll be able to do some reducing and factoring and so on. Okay, so you could do it that way, but not a very efficient way to do it. However, if you look at how I got this problem, just look at this. If I were to take this thing and subtract t squared and add t to the sixth over 6, or over 6 factorial, or 3 factorial, which is 6, then notice this is what I'm left with. So let's just go ahead and move this over to the other side, okay? So I'm going to subtract that, I'm going to add this, and here's my equal sign right here. See that? So, so I just did some algebra there. I moved these over to the other side. So notice now I have my numerator. And now I'm going to divide everything by t to the 10th. So t to the 10th right there. And that divides out so that this now becomes a 1. And this becomes t to the 4th. And this becomes t to the 8th, and so on. So you get that. And now you ask, what's the limit? There's my t to the 10th down there. What's the limit of this quantity as t goes to 0? Well, this is equal to this, so as t goes to 0, notice that all these things go away, and this is just equal to 1 over 5 factorial. What's 5 factorial? 120, I think. 1 over 120. See that? So there's a cool way to use Taylor series too. And sometimes these kinds of things come up, okay? They come up this way. In fact, I'll erase this one. One way again that one thing I'm doing with my differential equation class right now, or will be doing, is we are looking at the force of a pendulum and what the motion of the pendulum is. And let's see, I wasn't planning to do this. Let's see, doggone it, I wonder if I can do it. So here you have a pendulum, here you have the mass of it, and you have the tension of it right there, and you have the weight of it right there. And so, doggone it, let's see. I don't want to get into this. I haven't thought about this at all. But the point is, you look at the resultant forces. The tension's going to the resultant force is going to be in this direction, and that resultant force, if this angle is theta, that angle is the same as this, then that resultant force is just going to be mg, which is the weight going down, times, notice this is going to be the sine of theta. And that is equal to the mass times the acceleration. So here's your mass times the acceleration. Well, let's see, what's the acceleration? I guess I am doing this whole thing. So this distance right here, if this length right there is L, then then this distance that is going to be traveling is equal to L times theta, and so the velocity is the derivative of that, which is L. L doesn't change with time, but theta changes. That's going to be the derivative of theta. Quite often, let me make sure you're still with me here. This is all good stuff. Yep, very good. Okay, so then the second derivative is going to be L times theta double prime, and so here's your acceleration. So it's going to be mass times acceleration, right there, and let's see, and this is a force going down, so it's going to be a negative over here. Okay, I'm not intending to do this all really carefully, but the point is, this is your differential equation. There's the differential equation that governs the motion of this pendulum, and which is just, as I say, it's mass times the acceleration is equal to the sum of the forces. Okay, the sum of the forces right there. So there it is. And so now, notice what you can do. You can divide everything through by m, which is interesting. It shows that the motion has nothing to do with the mass. And you're going to get theta double prime plus, if you bring this over, g over L times the sine of theta is equal to 0. So there is a differential equation which models this motion right there. And you think, okay, that's great. How can you solve an equation which relates a function with its derivative? And most of the time, it's impossible. Just like if you were to ask me what's the antiderivative of something, most of the time it's impossible. Okay, so we spend all our time on ones that we know, but if you just come up with one out of nowhere, it's more than likely you can't do it. Same thing here. If you just come up with one, quite often that comes from the real world, quite often you can't do it. So you can't do that one, but here's what you can do. Here's what you can do. You say, hey, sine of theta is equal to what? Theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial and so on. Make sure you can see that. Okay? So the point is, as long as theta is small, and remember theta is measured in radians, and so if you're only 15 degrees, you take 15 degrees times pi and divide it by 180, it's going to be a fairly small number, okay? So if you're just moving back and forth 15 degrees like maybe the pendulum of a grandfather clock would be, then then theta is a small number. And notice when theta is a small number, look at this. The sine of theta is pretty close to theta because this number here is a small number and you're cubing it and then you're dividing it by 6, no less. So all this stuff is pretty small, pretty insignificant. And that's why we say when we interested in the rate at which a pendulum is moving back and forth, we have the proviso that it's got to be an angle that's close to 0, that's small. And as long as it's close to 0, we make that approximation, and we just replace that with theta. And so we replace that with theta, and then that's the differential equation which we can solve, and then everyone is hunky-dory. We go out and do it from there, okay? So just another example of where Taylor series are used to really be able to solve practical problems, okay? So that's that one. Here's the last thing I want to do. Oh, yes, doggone it. Everything is just falling right into place here. So now I can get rid of this, get rid of all of these. Couple more reminders. Okay, so I just mentioned to you just now that it's impossible to find the antiderivative of e to the x squared or e to the negative x squared, okay? If I say find the area underneath that thing, what does that look like, by the way? That looks like this. It looks very similar to that Cauchy curve that I had up here earlier, 1 over 1 plus x squared. If I say find the area of that thing from 1 to 3, you'd be stuck, okay? You can't find the antiderivative. If we had the antiderivative, we'd evaluate it at 3 and 1 and subtract the one from the other, and we'd be all set. Can't do it, okay? Can't do it. So and that's really a shame because this is, I think I've mentioned maybe earlier in this course, maybe not, that's probably the single most important function in all of mathematics, okay? Because that is your bell-shaped curve, which is used by statisticians whenever they want to figure out what's the likelihood of someone's IQ or someone's height or the velocity of atoms, of molecules, all sorts of things when you have just a distribution. Cool. I'm glad I brought this home from the office. Look at here. Here is this little gizmo with a whole bunch of little tiny ball bearings right there, and I've got a whole series of little pegs here where these ball bearings hit a peg, and they just as likely bounce off the peg and to the left as they do to the right. And watch what happens when I turn the thing over and they all go. Can you see that? Look at there. They all they form a normal distribution from that e to the x, e to the negative x squared function. There it is right there. So that's the reason why this is so important, because when you look at probabilities of things, this becomes really important. So my point is we want to know what the area underneath that is from, say, one point to another. There are a couple ways to do it. One way is to, it's called the Monte Carlo method. You just basically, if say we're interested in the area from 0 to 1/2. Okay, we want the area from there to there. We want to know what's the probability that the speed of an electron will be somewhere from whatever, net 0 to 1/2 or something like that. Not an electron, but of a molecule. Okay, so we want to find this region right in there. The area underneath the whole thing is 1 over the square root of 2 pi, I believe, something like that. So we basically need to know what that proportion is right there. So anyway, one way to do it is called the Monte Carlo method, where you just get a computer to randomly put this thing in a box. This height is 1 right there, and so this rectangle right there is 1/2 by 1. So the area of this box is 1/2. And you ask this computer to just randomly put dots all through that region. And then you count what percentage of those things lie under the curve. And the percentage that lie under the curve, just by making a ratio, you can get an approximation for what this area is, okay? So my point is, it's kind of a crude method, okay? It works, but you have to have a computer that will really give you random numbers, which nothing ever really does. And also, you need to do maybe hundreds of thousands of them just to get an approximation. And then how close are you? Well, then that's another whole problem, okay? So let me show you a far better way to do it, okay? Using Taylor series again, okay? So here's what we do. We start off with e to the x. Let me rewrite it here. So get this back up here. This is the function y equals e to the negative x squared. So we start with e to the x is equal to, what was it? It was x to the n over n factorial. Okay? And now we want to find the Taylor series for e to the negative x squared. So here we go. So e to the negative, I'll write it as negative t squared. So I'm going to replace x with a negative t squared. And what do we get? We're going to get summation negative t squared to the n power all over n factorial, n going from 0 to infinity, which if I want to, I can make it look a little nicer. Negative 1 to the n, t to the 2n, all over n factorial, n going from 0 to infinity. So there it is right there. Okay? So there's the Taylor series. That was easy to get. That converges to this function right there. And that's going to converge on the whole real line because the original one did. All I did was change the look of the variable, so it's going to converge on the whole real line there. That's all fine. Okay, that's all well and good. Now what? Now I want the area of that thing from 0 to 1/2. So I basically want this right here. See that? That's what I'm after. So that's what we can do right here. I take the integral from 0 to 1/2 of that right there. Okay, make sure I'm doing this right. That looks good. And now, do you remember what we learned a couple sections ago? You can interchange the order of the integration and the summation. And so we get what? We pull the summation out here. And here's our integration. We're going to have t squared, or t to the 2n rather. Notice that these things here have nothing to do with the integration, so I can bring those out in front of that. And I just have that dt from 0 to 1/2. Look how easy this is being right here. So now what? This is going to be the summation -1 to the n all over n factorial. And what's the antiderivative of this? It's going to be t to the 2n plus 1 all divided by 2n plus 1. Agreed? And now I want to evaluate that from 0 to 1/2. And this thing goes from 0 to infinity. So what do we get? Stick a 1/2 in there, you're going to get 0 to infinity, -1 to the n factorial, 2n plus 1. Finally, when you put a 1/2 in there for t, you're going to have 1 to those powers, which are all 1, all over 2 to those powers. So it's going to be 2 to the 2n plus 1. And so that's what you're going to get when you stick in the 1/2. When you stick in the 0, notice they're all going to be 0. So there it is right there. So voila, look at this. We've got ourselves an infinite series that converges to what we want, which is this area right there. And not only is it an infinite series, but it's an alternating infinite series. Okay? Why is that important? Because, let's see what happens. When you stick in n equals 0, what are you going to get? You're going to get 0 factorial is 1, you're going to get a 1 there, 2 to the 0 power 0 there, you're just going to get 2 to the 1. It looks like it's going to be 1/2 if I do that carefully. Now, when n is equal to 1, what do we get? It's going to be negative. It's going to be 3, and this is 1. So that's going to be 2 to the 3rd. 2 to the 3rd is 8. 8 times 3 is 24. 1 over 24. Okay, when n is equal to 2, what are we going to get? It's going to be positive. It's going to be 2 factorial, which is 2. 2 here is going to be a 5. 2 here is also going to be a 5. 2 to the 5th is 32. So 32 times 2 is 64. 64 times 5 is what? 320 is going to be plus 1 over 320. What happens when this is 1, this is 0, 1, and 2? What happens when n is equal to 3? What am I going to get? It's going to be negative. It's going to be 1 over, it's going to be 3 factorial, which is 6. 3, that's going to be a 7. And then this is going to be 2 to the 7th. Okay, which is getting to be kind of big. What happens when n is 4? You're going to get 1 over 4 factorial. I'll write it as 4 factorial. And then 9. And then 2 to the 9th. Okay, what happens when it's 5? It's going to be minus 1 over 5 factorial. This is going to be 11. And 2 to the 11th. And now let me remind you of what we learned about alternating series. If you want to know what this series converges to, remember what an alternating series does? It just keeps bouncing back. You first go there, and then you go there, and then you go here, and then you go there, and you keep bouncing back and forth about the limit. So if I were to stop right there, how close am I to the actual value of this thing? I'm that close right there. And look at that. That's 2 to the 11th. That's what, 2,000? I mean, this is a very small number already. You go just a couple more out, and you're as close as you're ever going to want in life, and you just got it very easily through this thing. Okay, so there is a really neat use of power series and Taylor series in order to find, again, very practical problems that are needed in life. Okay, so a lot of good stuff there. Doggone it, I wish I taught this stuff daily. Just the best stuff in the world. The last thing I just want to mention to you, which has nothing to do with this, is that there's another whole way of representing functions other than Taylor series. Okay? In particular, there are a whole lot of things in life which are periodic in nature. And so if you look at your heartbeat, you know, I don't know exactly what it looks like, but maybe something like that, or various things like that. Then the best way to model these things is not with polynomials, but with functions that are themselves periodic. And of course, the ones we know of that are the sine and cosine. And so that's called not Taylor series, but it's called Fourier series. Again, I don't remember how to spell it. It's called Fourier series. So we're not going to get into it at all, but just want to tell you, if you check out Fourier series, you see another whole way of representing functions. And again, this is super important in the digital world of music and so on. Basically, you take a musical wave and you just write that in terms of the Fourier series, and then all you have to do is include what the constants are in front of those Fourier series, in front of those sines and cosines, and you got all the information you need in order to get your sound back. Okay, so anyone who's into music has heard of Fourier series, Fourier transforms, and such. Okay, very good. I haven't decided yet. Either this is the very last video, or else I might have another video which just again goes ahead and just says what else is sometime. I might as well do it right here. No reason to have another whole video. So so basically, this is a typical Calc 2 course, what we've just covered here, and the other things that are sometimes in there. I guess we've done parametric equations. We've done polar coordinates. Yeah, we've done most all the stuff that's in there. The one thing that we haven't done is differential equations. And some Calc 2 courses include, you know, maybe a whole section on differential equations. I would include that here, but I'm going to start another whole series of lectures on differential equations probably tomorrow. Okay, so that'll be under a course called DEs or something like that. So if you want that material, and if that is something which is included in your Calc 2 course, you can just jump onto that and get it from there. So thanks for your listening. Hopefully you got a little bit of the excitement of what there is in the world of Calc 2. To me, this is things going off to infinity. All the practical applications of this stuff is just the best stuff in the world. So hopefully you got a little glimpse of it. Very good.